also on behalf of my co-authors, Simone and Luca, from the University of Trento, I'm going to present this paper that we proposed called A Comparison of Deep Learning Inference Engines for Embedded Real-Time Audio Classification. Now, we have seen that recent advancements in deep learning obviously have shown great potential for many applications, including audio and sound. And this goes together also with the availability of increasingly powerful embedded computers in the last years. And these two factors contributed to many deep learning framework developers to come up with their own inference engines. These are basically, most of the times, C++ libraries that allows us to take a pre-trained neural network model and run it in an optimized way, mostly for resource-constrained contexts, such as edge computing or in embedded devices, but it can also work for an audio plugin. However, we have seen also in research a lot of confusion around the use of these inference engines and the commercial ones with real-time audio processing and also audio classification. So even we really, there is no clear knowledge on, there was no clear knowledge on which of these can run in real time without, in real-time audio callbacks without allocating memory, without waiting on mutexes or more, and which of these are less resource hungry. So if we take the same neural network model, are some of these going to be more efficient than others, or is it the same? So in this paper, we presented a comparison of 4 available deep learning inference engines for real-time audio classification, and we did that on the CPU of an embedded single-board computer. Now, why classification? Well, in our case, it comes from our background. We are developing a smart musical instrument in the form of a guitar that can recognize in real time the expressive technique that a musician is using. And we want to do that also inside an embedded device, because then we want to embed this computing device inside the instrument itself. It's taking the audio from the pickups, so it's all self-contained, and it can also influence, for example, the generation of audio through this information of expressive techniques. And our device of choice was a Raspberry Pi 4, so only a CPU, not GPU, also running a real-time audio operating system, the ELK audio operating system for audio. The inference engines that we decided to compare are the most popular that we are seeing in research, which are TensorFlow Lite, the Lite alternative from TensorFlow, the PyTorch with the Torch script environment, the ONNX runtime, and finally RT-Neural. Now, someone already mentioned RT-Neural. This is a way smaller project than all the others. It's developed by one person, and it was developed towards audio. And it's considerably more limited than the other, but this is a very specific one for audio. And we have seen that a lot of people also in research went on to implement their very own specific neural network for inference with linear algebra libraries, but then the issue is that that can be good for optimization, but then it's not flexible. If you want to change your structure, you need to change directly the code. So can we use these more generic inference engines? Well, we tried that, and we wanted to test it, first of all, with one model that is the one that, in our case, works the best. Now, it's not really important here, the application, but we take features from the first milliseconds of audio of each note, and then we have 8 classes as an output of this classification. Now, the first issue that we had is that, for example, RT-Neural does not support the batch normalization operation as of now. So we couldn't use this model for all the inference engines. So we went ahead and used this model B that is smaller and was from a previous iteration of our search. And this can be executed in all models. However, while we run model A and model B both in high priority threads that are not the real-time thread of audio processing, because that's allowed for our specific application, then we also wanted to have a model C that is only one hidden layer of model B that we can run entirely on the real-time thread to check whether these different inference engines are trying to allocate memory or do nested stuff. And we ended up with 13 different test configurations among these 3 models and 4 inference engines. And for RT-Neural, we have 2 different APIs, if you want, 2 different modes of loading a model. One is more flexible. The other one is considerably less flexible, and it's supposed to be quicker with small models. And we compare these inference engines according to 8 different metrics. First of all, real-time safety is one of the most important. We want to check that these inference engines with the same model are not going to allocate memory, they're not going to wait on mutexes for some reason. They're not designed for audio, most of these, so it might be the case. And we want to check that we can use those in audio callbacks. Then we have also model execution time. So if we take the same model, we convert it for each different format, for each different inference engine, are we able to run these models quicker with one of these, or is it going to change? And this is crucial in real time because this takes away time for the other processing operations. Then we also measure the usage of computational resources such as CPU and RAM over a longer period and averaged it. And we also measure the model and library footprint, so the size of the models converted for each different format, and the size of the libraries. This might be important in embedded devices where we want to use less memory. We also consider the supported operations by each inference engine. Basically, when we are training a neural network, we have a large palette of operations that we can use, and we don't want to be limited to then what will be the application scenario. We want to use the one that works the best, and then when we go to deploying it to an inference engine, we don't want to be limited. So we also account for that. And then in the end, we measured, we gave a score to the ease of use and quality of documentation of all of these. To wrap it up, which is, I think, really important for newcomers to understand what they're getting into. Now, for real-time safety, we measure that using basically monitoring the status of a real-time kernel inside our embedded device. Basically, the audio processing is handled in the real-time thread, since it's a real-time OS, and we can monitor the state, and we can also monitor when this kernel is switching to the normal Linux kernel because we are doing something that is not allowed. And we did that by running the Model C, which is small. It takes less time than the others, but we want to just check for like memory location and that stuff. Very interestingly, all the inference engines were able to perform inference in real time without memory location, mutexes, or unsafe operations. There are some tricks. There are some tricks since both Turchet and INF runtime in different ways. They were trying to allocate memory on their very first execution, and then they stopped. So that's a good thing. So we can prime these engines by running a single operation at the very first execution of our real-time callback, and then we are good. They're not going to then create other mod switches, which was interesting. Then we evaluated the time. We have two graphs because, two bar plots because we have measured the time of execution in a standalone environment by running with mock-up data, a lot of times the same engines with the different models. And we also have done that on the deployment, plugin deployment software, where we have also the overhead of input-output audio and then processing, extracting features. So we have some overhead, but the results are very similar. This is expressed in microseconds. And we go from the bigger model, obviously, to the smaller model. And we have seen that the blue and green are TensorFlow Lite and ONNX runtime. And we've seen that those were the quickest one to execute the same models. It's still the same models for model A, B, and C. So they were like the quickest, closely followed actually by RT-Neural. So interestingly, RT-Neural, in this case with these models, which might be bigger than the intended case for that library, wasn't exactly quicker than the other. In some cases, it was a little bit quicker. In some cases, it was not. Interestingly also, the two different environments, one is allocating basically the model structure in the stack. We don't see a difference in performance with these kind of models. And so that was interesting. What we can see from this graph is that Turchet from PyTorch was the slowest one among the others. Now we also measured the usage of computational resources such as CPU and RAM over a longer period, which was a less informative metric, which was average over a low rate of operations. But we found that Turchet still uses a high amount of RAM, which confirms our previous results, and also ONNX uses slightly more CPU on larger models. We also measure very easily the model footprints of the size of each model, because even if we take the same model, we have to convert it for different formats for each inference engine. Now we see that the commercial solutions all use have a very similar size, which might be due to a similar binary compression or something. Still, it's very good. However, RT neural is considerably bigger than these models are considerably bigger than the other because they use a JSON encoding, which is human readable. If you want to use that, it's good, but then it's not compact. But one could go ahead and implement the raw compression since it's open source. We also measure the library size, and here we see that while the blue and the green one that are always TensorFlow Lite and NX are the smallest one. TorchScript is considerably bigger, and we cannot even see RT neural. It's very compact for the operation that it allows us to do, which is a little bit unweighted by the fact that when we sum that to the size of the model, it's not any more competitive. So it would be a good idea to implement a simple compression method for the weights. And then finally, the last three metrics are the supported operations. We went to measure and count the operation out of a pool of operations that are the most used, and we mean types of neural network layers and types of activations that are the most popular ones and the one that you want to use in your palette. And we found that all the commercial solutions support 100% of them, so we give a 10 score to all of them. While RT neural only supports 57% of those. Well, its design is fair. It's a small project and they were designed towards audio processing, but that's a limitation that we need to take into account. Also, ease of use. TensorFlow Lite was the easiest one to use. Also, the other one were not that complex to use, and we did that. We got that score by me and the second authors giving a score to each part of the development with these inference engines, so compiling the libraries, converting the models, calling an inference or priming the model or instantiating the model. And the average ended up giving a high score to TensorFlow Lite and also a fair high score also to the other alternatives. While finally, for quality of documentation, TensorFlow Lite was still the best because it has a very good documentation, but also a lot of tutorials, which is good. And it's closely followed by ONNX runtime that has very good documentation, but few tutorials. Then RT neural has basically the documentation is only the README in the GitHub page, which is fair. It's still a small project, but then the score is obviously lower. And very interestingly, the documentation of TorchScript and PyTorch, which is a popular commercial solution, was lacking. So it got a low score. It was very complex to understand it at the beginning how to use it. So that was it. We want to point out the fact that there are limitations to our studies. We focus mainly on these four inference engines that are four of the most used, especially in audio, also considering RT neural. However, there are others. I'm thinking, for example, at Apache MX or something. But then we measured only these. Also, we focus only on feed-forward neural networks for our specific type of application. And also on execution of the CPU. It would be interesting to see difference with the recurrent neural networks or convolutions. We might have similar results with the recurrent neural networks, but then convolutions might be tricky, might have different optimizations. And then we focus only on a single, rather powerful single board computer, which at this moment is not really easy to get, the Raspberry Pi 4. In conclusion, this is a summary of our findings. First of all, general inference engines, we found that they can be used for real-time audio. There is no need for specialized solutions. They can work in real-time audio callbacks, and they can have competitive execution times. Also, we know that trained models can be converted to each engine format. So if you're working and training models in PyTorch, there is no need to really then change the way that you train the models. You can convert them. It's not easy across all the types of inference of frameworks, but it can be done, so you can decide the different inference engine. We found also that TensorFlow Lite, ONNX, and RT neural are the quickest among the other with very similar execution times. It depends still on the model and the type of device, and while TorchScript was considerably slower. Also, we found that RT neural is extremely lightweight. It has similar execution time to the others. However, it supports a very limited set of neural operators. So it's great if you need only those operators, but it's also a trade-off that needs to be taken into account. And last of all, especially for newcomers to the field and want to try and decide one of these to start loading their models, either on embedded devices or audio plugins, because that's possible. We have seen that TensorFlow Lite and NX are the most well documented and also easy to use. But overall, all of those were fairly easy to use, convert, and compile. This would be it for me. Thank you very much for your attention, and I will be done.
Excellent. So, any questions at this point? Yes.
Hi, thanks for the talk. Could you maybe briefly mention what are the licenses of these libraries?
This I'm not sure. I'm not sure about. I know that these are free to use, and we are looking at them from like a research, academia research perspective. So we went to the one that we can use for free, and we are still thinking about research. We're not thinking about deployment or selling some. So we didn't look into them. I know that, for example, RT-Neural is completely open source, but I'll need to look into the licenses.
All right. Here's another one.
Can you describe the specifications of the specific board that you were using and how like a laptop computer might have differences that would affect your results?
Well, the interesting thing is that we stuck with a single board computer that has a similar structure to a laptop computer. So we still have CPU and memory and file system as we are used to. So I think that the limitations are only on the amount of processing power, amount of frequency of the CPU, amount of cores, there are only 4 cores, and also the size of the RAM, which is quite good on this device, but it's still that. So I think that's similar. Also, one great advantage of using the device that we use, that we have a real-time operating system. We cannot have that. We do not have that on a laptop. So we are running the audio processing on a real-time thread. For our case, for example, Model A and Model B, we only did the base audio processing on the real-time thread and then offload the classification to another high priority thread. But still, if we want to run audio processing entirely on the real-time thread, that's an advantage over a laptop. So I think those are the differences, main one.
All right, thanks much. Now we must move on. Okay, thanks.
Thank you very much.